I randomly selected problem 3, problem 8, problem 10. They're a little heavy duty on the means part of it, but I just did a random int on my calculator and those are the 3 that came up. So I didn't have any real reason not to do them, so I did. That means that whatever I can't go over with you today is up to you to look back at what you did, compare it to the key, and see what needs to be fixed up. Now, if you're not taking the exam, you probably don't even need to listen to this video, so I lost a bunch of you just now. But the rest of you, it is up to you to take some ownership of your own studying program. And just like there's no possible way I could have graded all 10 of these for all 109 of you, I can't do everything for you for your exam prep. And I will just kind of put a little bit of reality onto the grades. They were pretty high in general, but that's because there's a lot of fluff in this assignment. So if you have a 95 or better, I mean, you can look at the minor little things that you did wrong and, something may have happened here and there and you can just fix it. If you're less than a 95, you may be showing a trend of doing something wrong habitually. So again, look it over and see what needs to be fixed. Ask me if you're not sure. If you're below a 90, then there's a good chance that there's something major that you're doing that you need to quit doing. So again, look over that. And if you're below an 80, then, I don't know what to say. You're just going to have to fix an awful lot. But I'm here to help you out as best I can. So let's scoot through this. Problem number 1, I did happen to, it did grab my notice. Remember that this is the formula that you have for calculating required sample size for a particular margin of error, which is just really the margin of error here where you have to find n. You've got to get the right z-star number and you've got to get the right p-star number. Here they don't reference a prior study, so it's 0.5 and then 1 minus that. And then you have to do your algebra right, which not everybody did, but most of you did. But the biggest problem was leaving your answer like this, the 270.603. Some of you said it was greater than or equal to that. Some of you just said that's what it equaled. But you cannot collect a sample like that with the 0.603 still attached to it. Anything below an integer gets bumped up. So if it had been 270, you would have said sample size is 270. That would keep you within the margin of error. If you go above that, don't round it, bump up. That way you'll stay within your required margin of error. Label it with units and context, context, context. Didn't pay too much attention to B because I wasn't grading it. Didn't pay too much attention to number 2, although it is classic match pairs, all right? Turns out number 3 is also classic match pairs, and I did grade this one. You can tell it's match pairs because they gave an identifier number to each of the batters, and each batter is being measured twice. That's a hallmark of match pairs. Still, I got a bunch of people that did it as a 2 sample. That's just going to happen, right? But going into the exam, make sure it doesn't. So you want to put the numbers for dominant in the first column. You want of your calculator. The numbers for the non-dominant in the second column, subtract them, and you work off of the differences. A 1 sample t-test on the differences. I had people defining your parameter correctly, but not putting mu of a difference. That little subscript d there is important, and it's important in your HO and HA. Ooh, why did I put another HO there? It should be HA. We'll pretend it's an A. All right, make sure it's not equal to because they're only asking you if there is a difference. Some of you put greater than or less than. It's just not equal to. All right, don't forget independent for just about everything. Don't forget your 10% rule. That's for just about everything. I ran across an exception. I'll talk to you about it later. And look, I had people that said there's 19 values, it's below 30, you can't check it for normality? Yeah, you can. You can graph it in a box plot and check for outliers, because you're going to accept pretty much anything that doesn't have outliers because of the robust nature of a t-test. It is for means, right? But I'm a little bit flexible with this one because there's no matched pairs for anything else. So, but it's nice to put the means on there. And I knew that you did a 2 sample. Instead of getting 47.4372, you got something like 7.9 something. Yep, that's not right. Okay, so you're going to fail to reject and so on. All right, didn't pay too much attention to number 4. Didn't pay too much attention to number 5. Again, be checking these things. Make sure that you're getting all of the required elements that I'm putting in my key. All right, number 6. I did not grade this one, but I did look at it. I kind of glanced at it as I was going through these to see what people did. All right, so I want to just kind of pull back and look at this a little closer so that maybe you can sort of figure out what the deal is with this. All right. So here you've got level of dissolved oxygen, DO, in a stream or river is an important indicator of a water's ability to support life, right? Oxygen, the more the better. So a dissolved oxygen level of 5 milligrams per liter puts the aquatic life at risk. Well, that's the only value that they give you that you could be writing HO and HA from, all right? So we're going to be stuck a little bit with, let's see if I can get this to right. All right, well, hold on a second. This doesn't seem to want to write. Let me see if I can pause this real quick. All right, I'm not sure why I couldn't get any color here, but let's go back to what we were saying. So again, this number up here is the only thing that we can use for HO and HA. So I'm just going to say that HO is that mu equals 5 milligrams per liter. All right. But think about that. Let me just go ahead and close this thing off here. I forgot to do that. So then my neat little trick will not work. So let's just consider this. What are we going to do with HA? Let's say mu is something less than or greater than 5 milligrams per liter. Okay, so here's the thing. If we're going to claim that HO equals 5 milligrams per liter, that centers this curve at 5. And I'm just going to go ahead and dump into here. Hopefully it'll work. All right, it did. Let me go ahead and get this back to what I need. Sorry about this. All right, so let's just think about that. If you go with less than, which a lot of you did for various reasons, then you're looking at what I just colored in here. If 5 is bad for dissolved oxygen, isn't everything else going to be bad also? Right? Because everything going to the left will be less than 5 milligrams per liter, and fish can't breathe, right? So everything here is good. All right? So to get the counter argument, you're going to go with greater than. All right? If you go with less than, you're going to say that equaling 5 milligrams per liter is bad. But everything less than that will be bad. You don't have a counter argument. So this is the only way that you can set it up. Now, the problem that you get beyond this that some of you really kind of freaked out about was if you locate 4.77, right? That's where your sample outcome is. That's your X bar. Get that? All right. So if you're looking at greater than, that means that you want the probability of being at 4.77 or higher, right? So we're talking about this much of your density curve. And so you're looking at an area that's not only 0.5 in the clear, but it's part of the yellow here. And you end up with a p-value equal 0.82 or something. And I know a lot of you looked at that and said, nope, all right, 0.82, Garner always says that anything that bigger is a mistake. It's a possible mistake. And it's true. It could be wrong. You know, it's something that ought to catch your eye, and you ought to just go back and say to yourself, look, I got to figure out if everything I've done up to this point justifies getting a p-value this big. And you know what? I drew it all out. I just did justify it. So this is a good value. If you looked at it and just said no and subtracted it from 1 and got like 0.17 and then changed that to less than, you still were stuck with the argument of this being bad and then everything below it being bad and not having a counter argument, even though you end up failing to reject HO and all that kind of thing. So you can't get this problem right if you don't get the p-value right. Now hopefully that helped. So let me shrink that down and come back here. So you also had to get the error, you know, so since I'm failing to reject HO, if I fail to reject HO and that's a mistake, that's a type 2 error. It means I'm accepting HO when it's false. And so the explanation is I believe that dissolved oxygen level won't support aquatic life when it actually can. All right, so I want to make sure that you can figure out the type 1, type 2 error, because I have a real strong suspicion you'll run into this on your AP exam. Type 1 is rejecting HO when it's true. Type 2 is accepting it when it's false. Okay. Didn't look too close at number 7. Number 8 was one of the ones I graded, and most people figured out it was a 2-sample t-test for means. And so you have to define 2 mu's. You had to do less than, right? Or greater than, depending on how you defined mu1 and mu2. Right, SRS and independent samples, 10% rule. The normality was the issue. I believe there's 18 data points here and 16 here for a total of 34. So people said, oh, the sample size is 34, it's above 30, normality is approximated. But that's not true, right? You have 2 independent samples, both of which are below 30. You have to check them via graphic with a box plot or something, all right? Definitely a box plot to look for outliers, all right? Name it correctly, put the means on there, match pairs t-test for means, 2-sample t-test for means, 1-sample t-test for means. There are other kinds of t-tests. People that got this far typically did get the correct PT and degrees of freedom and everything and got the right conclusion. All right, number 9. I didn't look at it too closely, but you definitely have to be able to explain what a p-value means. All right, remember, here's your p-value. It's the probability of getting this big of a p-value or bigger given that HO is true. So in context, it's the probability that our sample proportion for female Olympic participation or higher occurred given that the true proportion is 42%. Okay? All right. Now number 10, we have a bunch of things to talk about here. It is 2-sample, right? So you have to define 2, mu1 and mu2. Don't put HO and HA. I know that they asked you for evidence, but you're still not writing HO and HA. It's a confidence interval. Just interpret it. All right? Part of the problem of putting HO and HA is that a lot of you who did that put that HA was greater than. Well, look, a confidence interval isn't a greater than, and it's not a less than. It's both. So the only way that this could even possibly match is if you had HA is that mu did not equal, or mu1 did not equal mu2. Okay? All right, so your assumptions. SRS and independent, populations are at least 10 times the sample size. You do have to check each one of these for outliers, the computer activity and the traditional. And you had to get them in your calculator correctly. Now it turns out 85 is an outlier. Right? It's not just visually, but it is in a modified box plot. But I would still get the wrong values in here. And it's just because of trying to dig the numbers out of a side-by-side stem plot like this or back-to-back. right? This is 10, this is 17, this is 20, 26, 28, but this is 24, 33, 33, 37, 37, 43, 43, 43, 46, 49, and so on. It's easy to make mistakes. All right, name it correctly. So you needed three things. You needed to do the usual spiel about being 95% confident in context. You had to look for 0, and really, since it's not there, both values were positive. I subtracted the standard from the computer-based, and that gave me both positive numbers. That implies that the computer-based gives you better outcomes. And you had to mention the outlier as a limitation. So you needed all three of those things. Okay,